Alright, so this is AEM 637 Theory of Elasticity, problem 418, number 6. Let's take a look at this problem and we'll work through it, but maybe the first thing to do is just figure out what they're asking for and what our approach is going to be. So this problem says, for the cantilevered beam, it is assumed that the elementary beam formulas hold. And there's the figure there for that. It looks like a cantilevered beam with a load on the end. Here's a stress distribution for sigma x, for tau x, y, and sigma y, sigma z, tau x, z, tau y, z are equal to 0. The material is elastic and deflections are small. We're also going to assume that it's an isotropic material. Determine whether all the requirements of three-dimensional elasticity theory are satisfied by this solution. If not, what is violated? All right, well, just looking at the solution, this is the stress that is sigma x right here, and it is the stress that is the normal stress in the beam. That's the beam bending stress. As we go further down the length of the beam, we have a higher bending moment. So that's why the x is in there. And then the y is in there because of the linear stress distribution from the top to the bottom surface of the beam. The tau xy gives us a shear stress distribution that's parabolic shaped. Then it says the other stresses are 0. All right, well, it says determine whether all the requirements of three-dimensional elasticity theory are satisfied by the solution. If not, what is violated? Well, let's take a look and see what the three-dimensional equations of elasticity are. All right, so we have equilibrium equations, which we can write in this fashion. So, for example, the partial of sigma x with respect to x plus the partial of tau xy with respect to y plus the partial of tau x z with respect to z plus a body force per volume is equal to an acceleration term times density. Now this would be the differential equations of motion. For equilibrium, this acceleration term would be 0, and we'd have equilibrium equations. Here are relationships that we have for an isotropic material, either the index notation form of Hooke's law or maybe the more usual form of Hooke's law. This one actually has a term that incorporates temperature change in it. And then over here are the compatibility equations. Right, so we have 3 that look like this, we have 3 that looks like this, or we can have it in index notation where we have here. Now, one of the things that we recently talked about around this section in our book are the Beltrami-Mitchell equations. So let's look at those. And the Beltrami-Mitchell equations are expressed here. And they're a combination of equilibrium and compatibility for an isotropic material. Now, in a lot of problems, the body force terms are either constant or they go away, and there's no temperature change, so this gets reduced quite dramatically. So we have a del squared sigma ij plus 1 over 1 plus nu, second partial of I1 with respect to xi and xj, where we can get these various terms in here. All right. The approach that I am going to take, we could use these equations, I think, shouldn't be a problem. The approach that I am going to take is I'm going to go back and I'm going to look at equilibrium and compatibility individually. All right. So let's get set up to do that. All right, so we'll take a look at our first one. We have neglecting body forces. We have the partial of sigma x with respect to x, so we can compute that. So we'd have 12py a cubed b. A cubed and b and p are all constants. Okay, and then the partial derivative of tau xy with respect to y. So let's see. We have a term that doesn't have y in it. That's the leading term here. So we have 3p times 4. Then we take the partial derivative. We're going to get a 2y. And then we'll have 2a cubed b. So let's see, the 2's cancel out. We're left with, there should be a minus sign in here. We're left with 12 py over a cubed b. Okay, so that does indeed equal to 0 for that particular one. Now the others, let's see what else we have here. So we can have the partial of tau. We can go yx with respect to x plus the partial of sigma y with respect to y plus the partial derivative of tau yz with respect to z. Now xy and yx are the same. Just easier for me to remember this equilibrium equation, write it down this way. So the partial derivative of tau xy with respect to y is equal, with respect to x, is equal to 0. And then, we don't get any other contributions from these other terms. So that one is satisfied. And then we have the last one, the partial of tau zx with respect to x plus the partial derivative of tau zy with respect to y. Alright, and then the last term here, if I didn't say it, plus partial of tau zy with respect to y, and the last term is partial of sigma z with respect to z. And we don't have any tau zx, we don't have any tau zy, we don't have any sigma z. So that one is satisfied. Alright, so equilibrium is satisfied. Alright, now that's not the only thing that needs to be satisfied. We also need to make sure that we're satisfying compatibility. So let me save this page, and then we'll bring those compatibility equations and we'll check those over. Now we also will want to convert these stresses into strains before we do that. Alright, and so we're going to calculate our epsilon x. We're going to use our 3D Hooke's law, which is going to be sigma x over E, and then of course minus nu sigma y over E minus nu sigma z over E. Sigma y and sigma z are 0, so what we're left with is sigma x over E, which will be 12 p xy a cubed b over E. Of course, you could use the version of this with the Lemay constants. Now, epsilon y is going to be sigma y over E minus nu sigma x over E minus nu sigma z over E. And the only term that will be left will be the one that has sigma x in it. So this is going to be minus nu 12 p x y over a cubed b times E. And if we want to use our number notation, this would be like epsilon 1, 1. This would be like epsilon 2, 2. And then epsilon z, of course, would be sigma z over E minus nu sigma x over E minus nu sigma y over E. And then we're going to be left with the same term, minus nu 12 pxy over a cubed b over E. That would be epsilon 3, 3. Now the shearing strain, gamma xy, or it would be 2 times the tensor shearing strain, epsilon xy, would be equal to tau xy over g, which would be equal to 3p a squared minus 4y squared over 2a cubed b over g. Or if we want to express it in terms of E and nu, we can rewrite g as E over 2 divided by 1 plus nu. So if we want epsilon xy, or epsilon 1, 2, we would take this and divide it by 2. This 2 and this 2 cancels out. We would end up with 3 halves p a squared minus 4y squared, 1 plus nu, and then we would have a cubed b over e. All right, let's save this page and then we'll clean this up just a little bit and bring our compatibility equations into this. All right, so here's the first 3 of our equations. So it's this first one starts out with the second partial derivative of epsilon 1 with respect to x2 twice, or it's the second partial of epsilon x with respect to y twice. There's only one y in here, so okay, that's 0. Second partial of epsilon 2 with respect to x twice. Okay, that's 0. And then the second partial of epsilon xy with respect to x and y. Let's check that out. So it would be 2 times 3 halves p one plus nu a cubed b e. This doesn't have any x in it, so I guess that would be equal to 0. Okay, so that one does check out. All right, let's try this one. And maybe we should just write down these partial derivatives here, but second partial of epsilon 1 with respect to z, okay, so that's 0. Second partial of epsilon z with respect to x1, which would be x. It's only first order, so that would be 0. Then we have no strain there, so that checks. Second partial of epsilon 2 with respect to z, that is 0, plus the second partial of epsilon z with respect to y. Since it's the second partial, that's 0. And then we have the 2 times the second partial of epsilon 2, 3, that would be yz. We don't have any yz, so all 3 of those are okay. All right, now let's check the next 3. All right, so let's check the next 3. And as you notice, I'm skipping over a little bit of the details here, taking these partial derivatives. For a homework assignment, you should probably be a little bit more careful and compute all these partial derivatives one at a time. All right, so now we got the second partial derivative of epsilon 1 with respect to y and z. There's no z in there, so that one for first term is 0. Second partial derivative of epsilon 2, 3. We don't have any 2, 3, so that's 0. We don't have any epsilon 1, 3, so that is 0. We do have an epsilon 1, 2, but there's no z term in it, so that's 0. So that one checks out. Second partial derivative of epsilon 2, 2 with respect to x and z. There's no z, so that one goes away. Second partial derivative of epsilon xz. There's no xz, so that's 0. Second partial derivative of epsilon 2, 3. There's no 2, 3, so that's 0. Okay, now let's check this one. Second partial derivative of epsilon 1, 2. We do have an epsilon 1, 2, but it has no z term in it. This is a partial derivative with respect to y and z, so that one is 0. So that one checks out. On to the last one. Second partial of epsilon 3, 3 with respect to x and y. Now we actually will get something here for that. This is first order in x and y, so the second partial of this should be minus nu times 12p over a cubed b e. Then we have the second partial derivative of epsilon 1, 2 with respect to z. Okay, well that's going to be 0. And then we have the second partial derivative of epsilon xz. Well, there's no epsilon xz, so that is 0. And then finally we have the second partial derivative of epsilon 2, 3 with respect to x and z, and there is no epsilon 2, 3. Okay, so we have found a violation here. So compatibility not satisfied. And it's because of the epsilon z term. Now the epsilon z would be the strain that is out of the page. So our traditional mechanics of materials solution has a problem with it for that particular compatibility equation. That means if we were to plot the strain fields, there might be some double valuedness or something like that going on in some particular spots. So this is a very good mechanics of materials stress solution, but it's not an appropriate fully three-dimensional theory of elasticity solution. Now there is one other thing that we need to check and understand, and we need to make sure that the boundary conditions are satisfied. This wasn't explicitly stated, but we do need to check the boundary conditions are satisfied. What do I mean by that? Here's a force on the end of the beam. That force comes from the shear stress distribution. So I'll let you do the work. If we were to take an area integral of tau xy dA, that should be equal to P. And there might be a minus sign thrown in here because this is down in the minus y direction. I'll let you work out that detail. Of course, the area integral would go from y from minus a over 2 to a over 2, and z would go from minus b over 2 to b over 2. So the equation would be 3p a squared minus 4y squared over 2a cubed b dy dz, and that should equal to p. I'll let you check that. And then over here at the wall, okay, the reaction is going to be, let me draw a free body diagram. The force, but there's also going to be a bending moment. Now, if we were to look at the stress distribution, let's see, the looks like the top would be in tension. And the bottom would be in compression, something like that. There would be a little bit of force acting on an element, and that little bit of force would be equal to sigma x dA, and the little bit of moment about this line would be equal to the y distance times the dF, which would be equal to y sigma x dA. So the moment should be equal to, put then a plus or a minus on this, an area integral of y times 12pxy a cubed b dA. Of course, you'd have the same limits, and this would be a double integral dy dz. And the moment should be equal to, they don't indicate the length of the beam, the moment should be equal to the p times the L. Okay, so when x is equal to L, then this ought to work out to be the force P times L. So those are some things that you should check in addition to check the boundary conditions and the applied loads in addition to the basic three-dimensional equations of elasticity. Alright, so that's it for this problem 4.18 number 6.